Okay, attendants, today we're going to have a look at a process called fractional distillation, which is really important for how we get hold of our hydrocarbons in the long run. So let's have a quick look at very simple ideas we're going to have to look at. So fractional distillation is a process where alkanes are separated out from crude oil into fractions. Now, hopefully you've watched the distillation video already and you remember that distillation is a process where you heat up two substances that are mixed together and you separate them off using the boiling point. So why do we need to do this with our alkanes? Why do we need to take our crude oil and separate it out into these things called fractions, which are chemicals that are a similar size to one another, alkanes that are all a similar size to one another? Why do we have to do this by fractional distillation and not just normal distillation?
So crude oil, guys, is a mixture of many hydrocarbons, hundreds of thousands of hydrocarbons potentially in a very small sample. So kind of like the molymod here, you will have lots of molecules of varying sizes. So we've got methane there, we've got an ethane, another ethane, hexane. They will all be mixed up together in the crude oil. Because there are multiple chemicals, so we've got methane, ethane, propane, butane, all the way up to carbon chains that could be hundreds of carbons long, are all mixed together in the crude oil. It would take far too long to do a simple distillation every time. So changing the boiling point just a tiny bit to get each separate one off would take an immensely long time, and you'd have to do it several times to make sure that you didn't get any of our one carbon molecules, any of our methanes and our ethanes still mixed together, because their boiling points are very close together. So we would use fractional distillation to simplify the process.
So because crude oil is a mixture of such a wide variety of alkanes, all we can do is separate them out into what we call fractions, so groups of molecules that are very similar in size. So as I said, methane and ethane have very similar boiling points, so they would be collected together in a fraction of their own. Some things we need to remember before we start talking about the process of fractional distillation. Small molecules will have a lower boiling point because they have weaker forces between the molecules, are lighter in colour, and they're easier to set fire to, which means they are more volatile. It's the sciencey word there, volatile, and they are more runny, they are less viscous. So they are more likely to turn into a gas overall. Larger molecules, again, will have a higher boiling point because they're so much bigger. They have much stronger forces between each of the molecules because they have more surface. They're much darker in colour. They're much harder to set fire to, so they're not volatile. And they're quite thick and viscous. So imagine the small molecules are more like water and the thicker molecules are more like honey or treacle, and then bitumen, which is one of our fractions, like tar, very viscous, very thick. So the process of fractional distillation. The first thing you would do is take your crude oil and put it into a heater. So this is completely separate from any of the fractional distillation column. So it's a separate little system where you would heat the crude oil up to an extremely high temperature, high enough that the vast majority of your alkanes have been turned into a gas. Only your very biggest alkanes would still be a liquid at this point. So you're raising it to an extremely high temperature in the heater and evaporating most of your alkanes. So most of the alkanes are going to be a gas at this point. And you then pass them into the fractional distillation column, which in a diagram would look a little bit like this. So the idea of the fractional distillation column is it will be hottest at the bottom. So this region down here is the hottest bit. Our heater would be pumping in our gases, our alkanes from here. So it is hottest at the bottom. And as you go up the column, it will get cooler and cooler. So the lowest temperature would be at the top here, and the highest temperature would be at the bottom here. And the idea is that as the molecules, the alkanes, come in from the heater. Those that are still liquid, our biggest alkanes, will of course trickle off at the bottom here. The others are all gas, and as you know, hot gases rise. They go up because of convection currents. And so the gases will start to rise up this fractional distillation column. Now, what will happen is at each section, it will slowly get cooler and cooler as the gases rise up the column. The idea is that when an alkane gets to the temperature that is its boiling point, the point where it would turn into a liquid, it will condense. It will turn back into a liquid because it's not hot enough for it to stay a gas anymore. So as the alkanes work up the fractional distillation column, they will slowly cool down. And then at this level, the next biggest set of alkanes will turn into a liquid, they'll condense. The others are still hot enough to remain a gas. Their boiling points are still lower, so they will carry on traveling up. And as each section is passed, a different fraction of the alkanes will be collected because they will condense back into a liquid because they have reached their boiling point. So at the top, the things with the lowest boiling point will be condensing. At the bottom, the things with the highest boiling points will be condensing. So our big molecules are going to be collected towards the bottom. Our small molecules are going to be collected towards the top. And actually, our smallest fraction, our methanes, our ethanes, our tiny ones, won't turn back into a liquid at all. And they are collected up the top here, still as a gas, because it won't get cold enough for them to condense into a liquid. So what we end up with is a fractionating column that looks like this ultimately. So here is our heater, everything is going in. The heater will be heating to around 300 degrees. And then, as you can see up the side, these are the names of the fractions that are collected at each level and roughly their boiling points, okay? So the thing to remember here is you need to know these fractions. So you're going to need to put these onto your notes at some point. You need to know the order of them. So bitumen is the biggest hydrocarbons, followed by fuel oil, lubricating oil, diesel, kerosene, naphtha, petrol. And refinery gases are our methane, ethane, propane, our tiny little alkanes, the one we mostly look at. Petrol is around the hexane to decane section, so our 6 to 10 bit. And then all of these are far bigger carbon chains than we talk about in our alkanes course. So note our small molecules are collected at the top with their low boiling point, their runniness, etc. Our large molecules with their high boiling point and their viscousness are collected at the bottom. So bitumen is a bigger molecule with a higher boiling point than petrol, which is a smaller molecule with a lower boiling point. The last thing you need to make a note of, guys, is some of the uses of each of these fractions. So methane, ethane, propane, you know we use it as gas. It comes out the gas taps in the science labs. Petrol for cars. Naphtha is used generally in the production of other chemicals for making pharmaceuticals, things like that. Kerosene is jet fuel, so plain fuel, diesel for diesel engines. Lubricating oil is things like Vaselines, waxes, unnaturally made candles, that kind of things. Fuel oil is generally used for ships or in some very old houses, central heating. And bitumen is the tar that they use to lie down on the roads. So hopefully you should have a reasonable idea of what fractional distillation is. The key things to remember is it's all about how big the molecules are, what their boiling points are, and the fact that they will condense as they travel up the fractional distillation column when they reach their boiling point and turn back into a liquid.